Don't know how to do it, huh? Okay, this good news is this is pretty easy.
Does it have anything to do with what we were doing before?
Not really.
Oh, fantastic.
Yeah.
Does it have anything to do with it?
Nothing to do with optimization. Okay, so what I want to do here, I want to show you a way that we can make a real simple approximation to allow us to calculate differences in quantities. And so really there's very little calculus involved in this, just some minor differentiation. But this is a big deal in especially in physics. In physics, we're always looking to try to find simple ways to model something. To get not exact answers, but approximate answers that are pretty good. And what we're going to take advantage of here is something called local linearity. That's local linearity. Now, and what that means is just that if a function is not too wild and crazy, if we confine ourselves to being in a relatively small part of the curve, so in other words, values, say we're going to pick a certain value on this curve f, x, if we confine ourselves to values of x in the neighborhood of x, so immediately around that area, then what we find is that the function is not that different from the linear approximation of the function, which for us is just a tangent line. So you guys have really been doing this already all year. I've given you, and you'll remember this, and hopefully I haven't blocked it all out. You remember I've given you lots of problems where it's asked you to find the equation of the tangent line of a function at a certain value of x, right? I mean, you've done a lot of those. Okay, so that's really all we're doing here. And wouldn't you agree that even though the blue curve and the black curve and the blue line diverge a lot when you get far away from x, if we're relatively close, if we kind of just stick right in here, they match up pretty well, don't they? Right? And that's going to be the case with any curve. If you zoom in on it, it's going to start to lose its curvature and start to look more linear, right? As long as the curve is smooth, if it's not, doesn't have sharp corners or something wacky like that, right? So we want to take advantage of this and say, okay, let's say that we want to estimate how much the curve is changing when x changes by a little bit. In reality, if we do that, the actual amount that the curve has changed, we might call, if we call this distance right here, the amount that x is changing, we could call that, for example, delta x, right? Delta, or let's call it dx.
I don't like delta.
We really don't want delta, we want dx. Well, we'll make these, d meaning small. Usually when we say delta versus d, delta means pretty big, d means pretty small. So we'll call it dx. The actual amount that the curve is changing, which is right there, we could call dy, right? And we can find that. That's really just equal to, if I find the coordinates of this point right here, if this is dx, what are the coordinates of that point right there? If this is x and this is dx, yeah, so the x coordinate is just x plus dx, and the y coordinate would be what? Say it again. F of x plus dx. Sure, we'll just evaluate the function at this new value of x. Right? And if we want to define, for example, how much the function has changed, we could just subtract those y values, right? But sometimes functions can be pretty nasty, and we don't like to have to go through the process of evaluating them twice. I mean, sometimes it's a hassle to evaluate the function if it's a big, long, nasty function. And so sometimes we'll choose to, I really should have made those black. That would have been a lot smarter. Well, I didn't, sorry. Perhaps it's easier to say, well, instead of knowing exactly how much the function changed, let's just approximate that by the change in this tangent line instead, because they're pretty close, right? Now, because this is a line, instead of calling this f of x, we're going to call this the linearization of the function, and we'll call it capital L of x, L for linear. Okay? And that's just going to be our linear model. Lines are easy to work with, though, right? The slopes don't change. It's really simple to calculate how much a line is increasing compared to a curve, right? So let's just do the math here. If we're going to call this, instead of dy, let's call this dl. Okay? What is dl? How could we find that? Any ideas?
Rush out.
Now, I'm going to give you a little subtle hint here. Maybe it's not so subtle. Let's sort of focus on this triangle right here. I might even call that, what's a right triangle? What kind of triangle would we have probably called that in Algebra 1?
Right.
A right triangle. But if we're talking about how much it's changing,
No, get that. No.
if I want to know how much this has changed, I could even maybe call that the rise in the function and that the run, because I just said it. Oh. Is that what you're going to say?
That's what we just
Yeah,
said.
Oh, is it?
Before,
You must have said it quietly. Okay, so that looks like a slope triangle, doesn't it? Right? It's just a right triangle, but one leg is horizontal and one leg is vertical, right? And so I could just say then that the slope, which is really just the slope of the tangent to the curve, right? That's how we got that line. The linearization is the tangent line to the curve at our point of tangency, right? So the slope of the tangent line, which by the slope formula is just dl over dx, right? Oops. In the language of calculus is what? What is the slope of the tangent line? Remember, this is just f of x, right? This is our function f. Okay, good. So it's just a derivative of the function at the point of tangency, which don't we like to call that just f prime of x? Right? So this gets pretty simple, doesn't it, for us, because we know calculus. So dl then, if I just solve for dl, we come up with a pretty simple equation. dl, if I multiply both sides by dx, is just equal to f prime of x times dx, right? And that's our approximate change in the function, right? When we scoot over to the right or the left, dx could be negative, doesn't matter. If we scoot away from x by some amount dx, that's our approximation of how much the function is going to change. Okay? Get the idea? Okay, we can use this for lots of things, but one of the things that's most useful for us to be able to do with this is stuff like this. Like let's say we're going to manufacture ball bearings, all right? And our ball bearings need to be 0.7 inches in radius, but in manufacturing these things, there's a certain tolerance involved, and we can only build these things to within, with our current ball bearing technology that we're using, we can only build these things to within 1/100th of an inch, 1/100th of an inch. And so we want to know then, approximate. We want to know what's the approximate propagated air going to be? How much could the volume, based on our measurement air or our manufacturing air, radius air, how much is that going to push the volume up or down? Approximately, okay? Any ideas how we could do that? Well, if we wanted to calculate, well, what do you think? So here is what I just made a little graph as just kind of a visual crutch for you, but we know that the volume of a sphere I gave to you, that's just 4/3 pi r cubed. You all know that, right? This is the graph of 4/3 pi r cubed. If this is the point, and it is, this is the point r equals, because this is the r axis, isn't it? And this is the v axis. R equals 0.7, v equals whatever. I guess it's that, if I plug it into my function, right? We want to know, if I scoot that over a little bit, approximately how much is the blue function going to change? Well, it's approximated by the red linearization, right? We're just going to use that. So what could I do? Well, we had our formula, right? We said that
Yep, I agree, Caleb.
dl equals f prime of x dx. In this case, really, we have dl equals f prime of r dr, because r is our independent variable, right? Okay, so if we go back to our picture, when we said x, what we meant was, in this case, the center value or the measured value, right? And dx, which will be dr in our example, was just maybe the measurement error or the manufacturing error, right? Does that make sense? That's how much we're swinging from side to side around that center value that we're shooting for, right? So we could identify here r equals 0.7, right? What's dr going to be? Okay, and it's going to be plus or minus 0.01, isn't it? Plus or minus 0.01. And we can put units in if we want to. What is f of r? Right? Okay, does that make sense? Because in our case, the function that we're interested in exploring the variation in, right, is the volume function. We're trying to find how much is the volume changing, right? So f of r is just our volume function, 4/3 pi r cubed. Okay? And so really then, the actual change in volume is going to be approximated by dl, the linearization, okay, which is just based on our formula. Just f prime, and we could call it v of r, couldn't we? Right? We called it f, but might as well just call it v, how about? Because that's what it is, it's volume. Call it what it is. So then f prime of x in this specific situation would just become v prime of r times dr, right? That's a pretty easy derivative to take, right? If that's v of r, you tell me what's v prime of r. Yeah, we'll just bring the 3 down, cancels the 3 out front, right? So we get 4 pi r squared. So if we plug that stuff in, then we get, oops, v prime of r would be 4 pi r squared dr. Let's evaluate that at r equals 0.7 and dr equals plus or minus 0.01. Get our answer. We throw that in your calculator and tell me what you get. Let's just take it out to, how about 3 places?
Did we get that equation with dv times dl?
That just means, that's just our squiggly equal sign, means approximately equal to, right? So the change in volume is going to be approximated by, right? The change in volume is the amount that the actual blue.
I gotcha.
Oh,
I
the-
didn't
the-
realize there was a similarity sign.
Oh, there you go,
Next to
okay,
me on
yeah.
some of these. Gotcha.
So what do we get?
0.061.
0.0616, so 0.062 we'll say, and it's gonna be plus or minus, isn't it?
Yep.
Right? Now that's one other handy sort of artifact of using a linearization is that the approximate error that you get, or the propagated error, is gonna be symmetrical, because it's a line, right? That's not the case with the curve though, is it? The line, if I scoot to the, this is probably easier to see on this picture. If I scoot to the right or the left, the line is going to change by the same amount, isn't it?
Yeah.
Right? So if I go plus dx, that amount that the line changes is exactly the same as it would be if I backed up by dx, right? That's not the case with the curve because the curve is nonlinear. In this case, the curve is going to change more to the right and less to the left. And so it even makes it more complicated to get an exact answer here because there's more information that has to be communicated. Now, if it doesn't sit well with that this is an approximation, that's what it's meant to be. This is not meant to be an exact answer. If we need an exact answer, we could always just go back and find out, the difference in the functional values. But this is supposed to be something that's a quick way of sort of analyzing behavior of a curve, right? And the nice thing about the line is, wouldn't you agree that the amount that the blue line is changing, like we said, it's going to be a little bit too small on the right side, but a little bit too big on the left side? Doesn't that kind of sound like an average? Right? And so it does a nice job of averaging out the differences in the change in the curve on both sides. Okay, so it's a really handy thing that engineers make use of a lot, for example. All right, so back to our example. So we got an answer here. So dV is approximately plus or minus 0.062 cubic inches, right? That's how much the volume is gonna potentially change based on our little manufacturing error or our tolerance in building the ball bearings, right? Is that good or bad? How might you know? If I tell you that I'm going to, let's say I'm measuring a board, and I can measure the board to within I can measure the length of some structure to within a quarter of an inch. Is that good? Well, if the structure is a mile long, it's probably fine, right? Quarter inch is probably not going to be a huge deal breaker. But if the structure is half an inch long, that's probably not so good, right? And so you see my point is that it really is a relative question, isn't it? It depends on the size of the initial amount. And so in this case, all we'd have to do, a much more valuable way of looking at this is to look at what's called relative error instead of just propagated error, right? Relative error in this case would equal is going to be the change in the quantity, right? The propagated error divided by the quantity. Yeah, you always just divide it by the actual magnitude, and then you come up with a relative amount that's much more meaningful, right? Now, a couple ways you can do this. We found that, where's our formula? Right here. Okay, I'm going to transcribe that, put that on the next page. So, if we wanted to find, oops. Never mind. Build a new page here. Okay, so for our last example, we said that V equaled 4/3 pi r cubed. We said that dV equaled 4 pi r squared, right? If we wanted to calculate the relative error, dV over V, sure, we could go through the hassle of calculating dV like we did, right? We went through the whole process here of finding out what the propagated air and volume was, and then just dividing that amount by volume, which we initially calculated, right? That's going to work. Do you see maybe an easier way of doing that? Can I avoid having you do both of those complete calculations? Because most of the time, this is really what I'm after anyway. Most of the time, I don't really care what the actual propagated change in volume is going to be. I just want to know, for example, what percentage, what's the relative percentage error going to be? The volume's going to change by plus or minus what percent?
You use the formula that cancels out all of the
Yeah, why not?
Oh yeah, it uses R.
Why not, right? We know here that dV is equal to 4 pi r squared, and V is 4/3 pi r cubed. They're using the same variables. Why not just algebraically reduce that ratio? Right? So that just becomes, if I cancel everything out, the 4's cancel, the pi's cancel, and r squared cancels. And so on the top I get 1, on the bottom I get r over 3. So what does that simplify to? 3 over r, yeah. If I divide by a fraction, I just flip and multiply. Right? And so now all I've got to do is plug in one quantity, just r. Right? Let's hang on a second here. I forgot one thing. One thing missing. Was that not on our formula here? Oh, I forgot the dr. Right? Dr is important. You got to add the dr. So that's no big deal. The dr, it's just right here. It's just a little term that sits right there. Little factor, right? So on the top we get 3 dr over r. Okay? Now, that's pretty cool. Think what that just said. The relative propagated air and volume, then, we could think of as being 3 times the relative measurement error. That's interesting. Don't you think? You think what that's saying? If I scoot over, if we look back at our picture, if I scoot over on my graph to the right or the left by plus or minus 0.01, if r is being tweaked by that much, okay, then the amount that the blue function is going to change, the percentage change is going to be 3 times as big. Why do you suppose that is? Well, I guess because it's being cubed, and so it's a fairly aggressive function, right? That make sense? Okay. Now, whether or not you take advantage of that relationship, it's easy to plug the numbers in, right? If we want to find out what is the relative error, well, our answer is approximately equal to 3, and then dr was what, plus or minus 0.01? And r was, yeah, 0.7, right? And so we get an answer of plus or minus 0.03 over 7, which is what, as a decimal? Oh, 0.7, sorry.
Fantastic.
You're right.
What's the right thing?
0.043, which we probably want to write as a percent. So what is that as a percent? Plus or minus? Now that means something, doesn't it? That says something to us. So our error in manufacturing those ball bearings is going to result in potentially propagated air and volume of plus or minus 4.3%. Now that might be important because volume would be proportional to, for example, weight, right? So if you want to know how much the weight's going to vary in these things, that might be a big deal. That's how much it could vary. That may be too much, might be fine. But that's the critical piece of information that we probably needed to know in our ball bearing manufacturing business, right? Does that make sense?
Yes.
Try one.
Let's see.
Okay, I want you to tell me here what is, this time we have a cube, and the measurement error in measuring the side length of this cube is, well, we measure it to be 10.1 centimeters with a measurement error of plus or minus 0.1 centimeters. Okay, so I want to know what is the relative percentage error in calculating volume. Okay, what's X? So that's 10.1, isn't it? Right?
Yeah, okay.
So X is 10.1.
Is it not X?
Yeah, no, that's it. I was starting easy. What's dx? Plus or minus 0.1, so that's not much harder. What's f of x? Yeah, right, because we're calculating a volume here, aren't we? Right? Okay, so then what's f prime? 3x squared. Okay, and so all we need to know then, if we want to know what is the relative error in calculating volume, what's that going to look like? And so what's the ratio going to be in terms of volumes? What's the definition of relative error again? Change in, right? So change in the quantity, right? Divided by the quantity, right? That's probably, I'm sure that was a very clear question. So then what is dV? Well, 3x squared, right? We just calculated that. V is x cubed. And so I can cancel some stuff, right? And I just get what? Oh, oops, I forgot the, what is dV? X squared dx. and it's twice in a row, I forgot that, but remember where that comes from. It just comes from, this is an easy way to remember it. dv dx is just f prime, or we can even call it v prime, right? So dv is v prime of x dx. Now this, I haven't given you this word yet, but when we write something in that form, that's called the differential form of a derivative. When it's not written as a ratio of dv divided by dx, it's just written as dv equals v prime of x dx. Okay, that's called a differential. And all the derivative formulas that you currently know, all the derivative rules, can be rewritten very easily in differential form. We'll just take one as an example. For example, we know that if y equals sine x, right, then what's the derivative of y equal to? Cosine x, what? dx, right? Because dx equals cosine x, right? So I'd multiply both sides by dx. Get that, right? So the differential form of a derivative, we'd say, is the derivative of sine x is cosine x dx. There's nothing hard about that. All you're doing is you're just multiplying both sides by dx, right? Okay, and so it's nothing that, it's nothing new. So we just call it a differential. Okay, so what does this reduce to? Simplify to?
3 dx over x.
3 dx over x. So same result as before, because this also is a cubed function, right? Okay. And we could just plug in our stuff and get an answer. So relative error then is equal to 3 times plus or minus, what was it, 0.1?
Yeah.
Divided by, and here's something else. Notice that the units cancel. If I did include the units, it's plus or minus 0.1 cubic centimeters, right? Did we measure this in centimeters? I think we did, yeah. Right? Or centimeters, sorry. Because it's x, right? dx is plus or minus 0.01 centimeters. X is 10.1 centimeters. And so if I do include the units, look what happens. X is 10.1 centimeters. Look what happens. They cancel. Okay, that's good. In physics, we love unitless quantities because unitless quantities are they're in a way they're pure. Yeah, they're just relationships that are independent of what you're measuring it in, size, etc. Right? They're behavioral quantities, right? So that's good. We've got something that's an intrinsic relationship here, not dependent on any measurement stuff, right? Whatever units, etc. And we get for an answer then what?
100%.
So roughly as a percentage, what is that? 3% plus or minus, right? I guess it's probably that. You're saying?
Yeah.
So plus or minus 3%. That tells us something. Okay. Now, what if we said, okay, change this around a little bit. Let's say that we can't have a propagated volume error because we're building, I don't know what we're building these metal cubes for, I don't know what, paperweights, but they're really precise paperweights. And we can't have the volume vary by more than 2%. Okay, we have to decide how accurately do we need to measure these things. Because the more accurate the measurement, the more time and more money it takes. Right? So we want to know we don't want to overshoot. We don't want to waste money and measure them too accurately. We just want to measure them just accurately enough So if we change this problem around a little bit then, how could you approach that?
Solve for the VX.
Okay, so now, yeah, good. So this time we're saying that dv over v has to be less than or equal to, what did I say it was? 2%? Okay, we already did most of the work. Right, the dv and v aren't going to change, are they? Isn't v just still x cubed, and dv is still 3x squared dx? And so all the work we did in the prior problem still applies. We still get the answer 3dx over x, right? If we take those derivatives and just reduce that function, simplify the function. What did I say it was 3dx over x?
Yeah.
Okay, so now what?
Plug in the 0.02.
Good, because that's really what we're saying. It has to be less than or equal to that, right?
Yeah.
0.02. This is the only variable now. I could plug in 10.1 for x, right? Okay. Yeah, good. So 3dx over 10.1 has to be less than or equal to 0.02. And now we can just solve for that guy. So multiply by 10.1 over 3.
You get 0.067.
Okay. And that's roughly equal to what?
0.067.
Okay. And that would be a plus or minus, wouldn't it?
Wow.
How about that? That's pretty good. Okay, here's another good little parlor trick you can do. Impress all your friends at a party sometime. Pull out your cocktail napkin and impress them with your ability to approximate square roots. They'll love it. Won't they? Maybe in college they will.
Somebody get a calculator.
Yeah. Okay, so what if we wanted to approximate, say, the square root of 10? There's a way we can do this too. Okay, we could think of, and I'll go over this again, but I just want to leave you with this one. This, and it really works. This makes it really easy to make a good approximation. So the square root of 10, we could say, is equal to the square root of, what's a convenient perfect square close to 10? 9. Okay, so we could say that's roughly equivalent to, or it's exactly equal to, the square root of 9 plus 1, which is roughly equivalent to an approximation that we could make based on the square root function. Now that's the same thing as saying if we had, say, the function f of x equals the square root of x, right? And x equaled what and dx equaled what? What would be the point that we'd want to pick x to be a value where we could conveniently calculate, there we go. There's even better problem. Where we could conveniently calculate the y value, right? So we know the coordinates of that point on the curve, right? And then dx would be how much we're going to shift from that point. So now, what's your thinking? What would I choose x to be here? My function, the curve I'm using, I'm gonna linearize, is a square root function. 3. Well, 9, right? So 9 would be a convenient value, and dx is just going to be plus 1, right? Does that make sense? Okay. So then, the square root of 10 is just the square root of 9 plus 1. So that's, in terms of our function, that's equal to f of x plus dx, right? Now, we're going to approximate that by, that's approximately equal to f of x, which we know, right? plus dl. Everybody see that? Let me go back to my picture.
Oh, yeah, okay, I see what
I probably should have just copied this picture, shouldn't I?
Yeah.
It would have been nicer. But, right, so this part we know. We know that f of x, the square root of 9 is 3, right? We know that. What we're really looking for is how much more than 3 is the square root of 10 going to be? We know it's going to be 3 point something, right? How much? Well, the actual amount is dy, but that's hard to do in your head. This little linearization, though, might not be so bad if we want to find out how much the tangent line is changing, right? We have a formula for that, right there, right? The amount that the linearization changes is just f prime of x dx, right? Right? So f of x we said was the square root of x. So what's f prime of x? That's just x to the 1/2, right?
Yeah.
So what's f prime of x? So it'd be 1/2 x to the, okay, so the negative 1/2 means what? Negative 1/2 power means square root on the bottom. Everybody agree? And then I got a 1/2, so there's a 2 on the bottom. So that's really just equal to 1 over 2 times the square root of x. Right? Okay. So dl then is just f prime of x dx, which is 1 over, yeah, my writing kind of degraded there. 1 over 2 times the square root of x times dx. Well, let's just put the dx on top. And f of x, we know what that is. That's just the square root of x, right? So let's replace that. And you can do that in your head. That's you can, as a fraction at least. Making it into decimals a little bit harder. So what do we get? Our x value we said was 9, dx was 1. That's the amount that we're shifting from our known, our convenient value, right? And so this ends up being the square root of 9 plus 1 over 2 times the square root of 9. What? Isn't that just 3 1/6? Right? That's okay. So see if you can do this one. What's this? Approximate the square root of 24. Approximate the square root of 24. So what's the function going to be? You're approximating what? Okay, but it's square root, right? So f of x is going to be just square root of x.
Yeah.
X to the 1/2.
Yeah.
Okay, what would the value of x be? If we're trying to approximate this, okay, it'd be 25, wouldn't it? Good, because 25 is a perfect square. And what would dx be then?
Negative 1.
Negative 1. Yeah. So once you do this a couple times, you can literally just do this in your head. Because it's always the same, isn't it? I mean, f of x plus f prime of x dx, if it's a square root function, f prime of x dx is always just dx over the square root 2 times the square root of x. So 4.9,
Yeah.
right? 5 plus 1 over 2 times, or negative 1 over 2 times 5. Yeah. All right, we'll look at maybe a couple more quick problems, and then I'll put the assignment up. But that's it for the chapter.